Hey everybody, this is our lesson on covalent bonding, and by the end of this lesson you should be able to compare the relative strengths of ionic, covalent, and metallic bonds and infer the type of bond and chemical formula formed between the atoms. So we'll really focus on just the type of bond, not the chemical formula for now. But before you get started, you may want to go in and review dot structures and the octet rule. All right, so let's look at covalent bonding. So a couple terms we need to know before we get too far into this are monatomic. Remember the prefix mono means one, atomic atom, so one atom, and there's an example. We have diatomic, which means two. This should say two. I don't know why that says one here. Give me a second. So that should say two. Okay. And it says that a molecule is two or more atoms that are covalently bound together. And when we use the term molecule, you need to think of covalent compounds. For an ionic compound, we would use the phrase formula unit. We do have some elements that are known as diatomic elements, which means they naturally come as a pair. So I say that these are the socks of chemistry because they naturally come as a set. And that would be hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. These are also known as your lucky or diatomic 7. And then we have covalent bonds themselves. So the definition of that is the sharing of electrons. So this is really important to underline here. So this is the sharing of electrons when obtaining a full outer octet. And this is between two nonmetals. So this is just a quick GIF to show you kind of how that looks. All right, so now let's talk about types of covalent bonds. The first one we have is a single covalent bond, which means it's a single bond between two elements. And within that single bond, you are only sharing two electrons. You have double covalent bonds, so that would be two, obviously double. And if one shares two electrons, then a double will share 4. And then we have triple, which will share 6 electrons. In terms of strength and length, which we look at comparing these types of covalent bonds, for bond length, a triple is the shortest, double is the middle length, and single is the longest. I like to compare this to how well you know somebody. So if you know somebody just a little bit, like an acquaintance, you don't have a lot in common, you're not super close to them, but your best friend who you have a ton of stuff in common with, you're very close to them. And that's the same here. So a triple shares 6 electrons. That's 6 things they have in common. They're going to be very close. But a single only shares 2 electrons. That's 2 things they have in common. They're not going to be as close. And then bond strength is the opposite. So the longest bond, a single, is actually going to be the weakest bond. It's the easiest to break, where double is the middle and triple is the strongest. And then here just shows the formation of a single covalent bond. And here shows the formation of a triple covalent bond. Now let's talk about covalent dot structures. So we're pulling back in from Lewis dot structures at the beginning of the unit. First, you're going to count up the valence electrons on each element in the compound. Pay attention to the charge. So if I give you like a polyatomic ion, which just means a mini atom ion, and it's got a charge to it, then we look at adding or subtracting electrons where needed. Is that it? There we go. If it's in an ion, it does still go in brackets, just like we learned with ionic compounds. And you'll draw the individual dot structures first for each element. I'm sorry, my little click is not wanting to work. There we go. You connect single dots between elements to make a shared pair, and then you move those bonds to the middle. So I will always tell you when you're doing this, I'll say make buddies. And buddies means you partner up lone electrons to make a pair. You try not to split up lone pairs that are already partnered. So you don't split up buddies that are already formed unless absolutely necessary. And we'll talk about some examples where that's the case. Come on. Sorry, I'm trying to get this to work. There we go. And then we have what's called a coordinate covalent bond. And this is where one atom in the bond donates a pair of electrons to share. So in class, you may want to ask me about the pool house. That's like a weird example that I give to help this make sense. And then here shows you just a quick picture of how you would make those dot structures for a covalent bond. And then as you can tell here, let me X out of my picture, you can see this bottom one is a coordinate covalent, because if you look at oxygen, oxygen has, we're going to split that in half. So 2, 4, 6, 8 electrons, whereas carbon only has 2, 4, 6. So it's going to donate that pair in and they're going to share them. So now it's got 2, 4, 6, 8. 2, 4, 6, 8. Remember here as well, when you're drawing these dot structures out, you can draw dots, or that is equal to one line. So you could draw one line in between. So now let's do an example. So we want to draw the dot structure for CO2 and NO3 minus. First, you're going to add up all the valence electrons. So for CO2, we have a total of 16. For NO3 minus, we have a total of 24. 4 comes from the carbon. There are 2 oxygens, each with 6, which is 12. So that gives you 16. Nitrogen donates in 5. Oxygen, each oxygen has 6. So 5 plus 18 is 23, plus that 1 because of that negative charge there gives you the 24. So then you're going to draw the individual dot structures and make the buddies. Use brackets if needed if they've got a charge. So I'm going to, I should have the answer on here, but I'm going to go ahead and draw these out for you so you can see it. So you've got carbon with its 4 dots. You've got oxygen with their 6 electrons, and we're going to make buddies. So that means just start connecting the dots. Okay. So we connected those, and that's going to end up forming our final product, once we move the dots in, of CO2. Okay. The same thing for nitrogen. So we've got 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. 3, 4, 5, 6. So we're going to make buddies. I'm going to partner those up, partner those up, partner these up. And now this one is a little finicky because of just the way it's laid out. We do get to add 1 in because of that -1 charge. So I am going to actually just put that one right over here. Okay, just stick it wherever it needs to go. And then we can move electrons around. Once they have started to form these bonds, you can actually move them around on the entire molecule. So what we're going to do is we're going to take this pair, we're going to donate it into oxygen, and then take this lone electron and give it to our oxygen down here at the bottom. So you're going to end up with a dot structure that looks like this. So we've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Everything's got 8 and it's happy. I'm going to clear my screen, so I want you to pause right now so that you can write all of this down. And then just make sure, like I said, to add the dots and bonds together so that they equal the total number of valence electrons. So I want you to try this example here. Oh, wait. It's okay. Hold on. Let me see if I can go back. I don't think it's going to let me. Okay. So let's just go ahead through with the octet rule exceptions. So boron is an octet rule exception. It does only hold 6 electrons. That's all it can handle. So don't try to give it more than that. Phosphorus can hold 10 electrons, and then sulfur can hold up to 12. This is due to that empty d orbital that can hold extra electrons. So I like to say to think of this as like an inside jacket pocket. So you have jackets that have pockets on the inside. You never really use them for anything, but they're there if you need them for space. That's what your d orbital is. Doesn't have to be used, but it can be if necessary. So some examples here are BF3, PCl5, and SF6. And follow the same rules for drawing out these structures. I will say, when you're drawing out these structures on phosphorus and sulfur, you will end up splitting their lone pairs. So there's BF3, there's PCl5, and then here is, FS6, you would have saw it. So that's just a quick, it was a long video, but